Alright everyone, we are back and we are going to look at some examples of heat transfer and solve some heat transfer problems. Again, heat transfer, as you can see here, is governed by several different equations, and unfortunately this is not a heat transfer class, but we'll be covering some of the basics that we can set up some solutions. So heat transfer is governed by Fourier law, so we look at heat flux here, based on thermal conductivity and a temperature gradient, as we see here. So this is actually a very general equation for flux. So we're looking at a gradient, which is our gradient operator, and we'll take a look at that shortly. And then your kind of fundamental equation for heat transfer is this change in temperature, change in time. So this is a PDE. So this is a PDE that's second order in space and first order in time. So we can start to go ahead and solve some of these problems. So we can look at the steady state solutions. The steady state solution when temp does not vary as a function of time. So as such, you're going to find that basically this value goes to 0. And we could set two different boundary conditions. So if we're looking at basically heat in a rod, initial condition on the left side, or 0x, 20, 1, and then here we're only looking in 1D, so we can solve this problem. And you could plot the solution, and it's as you expect. Linear function, again, second order, two boundary conditions. You could also look at heat flow in a rod, but now time varying as well. So again, here's my heat equation. Again, this is telling me the derivative with respect to time, alpha derivative with respect to x2. You could also do that with grad. So you can also do basically grad of t as a function of tx with respect to x. That'll give you effectively, very similar thing. You want the second one, you need to do Laplacian. So Laplacian can give you something very, very, very similar. So anyways, we have our heat transfer equation. I can set my boundary conditions. So again, second order here. So I need two boundary conditions in space for all times. So these are fixed temperature boundary conditions. I have an initial condition. I'm just going to set my temperature to 0 initially, and I'm going to go ahead and solve. And so this will take some time, but you see my solution is going to be a function of x, and is also a function of t, as you can see in here. And it's going to be this kind of infinite sum of sines and cosines. So we'll let that, again, Mathematica is trying to figure out and solve, and basically going through all the different types of solutions that we can possibly kind of find. So bear with me. Again, not the most exciting part of the video, but informative nonetheless. The key thing here is you can see I take my heat equation, give me my boundary initial conditions, and I have my solution. So I could take the solution, I can look at the first 100 components, for example, and then I can look at my solution given these values, and now I can plot. And so I could see if I'm at t equals 0, time, if I have a high thermal conductivity, which we don't want to do that, but if I look at very, very short times, boundary conditions, fixed temperatures here and here, 0 everywhere else effectively, and then as I increase time, I approach my steady state solution. And I could approach it even faster if I increase my thermal conductivity as well. So there we go, our thermal diffusivity. So these are my functions. Again, you can look at those, play around with it, look at different values, and you can see how your solution changes depending on the number of those coefficients. You can solve the same function using very different notations here. So this is just what you're seeing. But again, same values effectively, same thing. And if we look at our solutions, I'm going to abort that evaluation because it's just going to take some time. If I look at my solution here, oops, ooh, it does not like that because I need to get it. Let me give it these values. Let me look at this. And now I can kind of show you that same type of solution, but with some different boundary conditions initially. So there you go. Now I could build and make some more complex problems here. So I could do insulated boundary conditions. So again, take my same heat equation, but now I have insulated boundary conditions, meaning 0 heat flux. So again, if we go all the way back up to our equation here, so if I have 0 heat flux, if I'm insulated, basically it's saying that my gradient is equal to 0 at those locations. So if I look at my boundary, I am insulated. I could set that derivative here equal to 0. So here, and then 1, the length of my condition. I could set initial condition again. I could solve my heat transfer equation. So we'll go ahead and jog through it one more time. But actually we won't have to, because I'll abort the evaluation again. But you could test out yourself, but you can find your solution again. So as I scroll through in time, insulated temperature boundary conditions, I should equilibrate. So if I'm completely insulated and I change that temperature, again, initially my temperature is a function of 30x, so basically linear function, but as I cool down or as I change time, it should equilibrate the straight line. And that will be the case, especially if I increase my thermal conductivity again. Excellent. So next time we're going to look at one of the suites that's available in Mathematica, which allows us to essentially solve for heat transfer problems using built-in functions and functionality here. So we'll explore that next time. Thanks. Bye.